Welcome back, everybody. Today we're going to be discussing one of my favorite games that I learned to play actually in therapy, and it is the best, worst, and average case game. It actually works really beautifully for our analysis of algorithms topic as well. I am such an anxious worrier, and all the time when there are scenarios or things going on, I'm always trying to prepare myself for the worst situation. Like, what's the worst possible thing that could happen? Now, in therapy, I learned you can't only play the worst case game, you have to play the best case and the average case game. And this holds true for our example in computer science and in this topic here. Imagine for a second that you're trying to find your keys, like you've lost them, you can't find them, you're going to be late for school. Sometimes when you go looking for them, they're right on the counter, you find them, it's the very first place that you check. Thank goodness now we won't be late. Other days, we have to check every single pocket, the bag, the car, the couch, the freezer, like who knows, right? Same searching method, but a very different amount of work. Algorithms behave in this exact same way. Now, keeping in mind, we're going to be talking about three perspectives on the same algorithm. We are going to be talking about first, well, maybe not first, but one of them is going to be our best case. This is our luckiest scenario, right? This is our best case scenario. Luckiest scenario. Finding those keys on the very, very first try. The next one is our worst case scenario. And this is going to be our unluckiest scenario. It's going to be we don't find them at all and we don't get to go to work and then we get fired, right? Our unluckiest scenario, it's in the very last possible place that we could look. And then the third scenario is our typical or our average case scenario. Average. And this is going to be more often than not when talking in terms of like data, it's random data often or a typical input. And we'll see examples of all of these, so don't worry about that. Typical input. There we go. Like I said, this is a game. I play this game all the time in therapy. And if you are like an anxious worrier like me, we're going to let ourselves play that worst case game all the time. And we forget about the other options. And it happens with computer scientists too. We care a lot about big O, and we learned about that last week. And big O is our worst case growth. But there are other scenarios that we need to consider. We need to consider the data that we might be working with. So by understanding this, we're going to be able to predict the performance of our algorithms a little bit better, and we can ground it in a really realistic way. Now, last lecture, we discussed the growth of an algorithm based on the input size of n. So when we were talking about asymptotic notation, I'll just write that down, asymptotic notation, we were talking about over an input size of n. There we go. Okay. Now we're going to talk about these three different cases, best, worst, and average, in terms of steps. So first we have our best case scenario in terms of steps. That would mean the minimum number of steps possible. Our next scenario that we outlined was worst case, right? And this will be the maximum number of steps possible. And when we're talking about steps, we're talking about like accesses to heap memory kind of steps, the things that we did in our previous videos. And then we have our typical and our average case again here. And this one is going to be most of the time number of steps. It's a little bit more abstract, that one, but that's okay. What we're talking about, though, for each of these is more specifically what input values, not size, we're actually talking about the values of our input for a minute here, allow us to achieve these cases. That's really the question we have right now. We're not actually talking about math, and it maybe the average case seems a little abstract right now, and that's okay, we'll get there. But we really are talking about actual input and thinking about the actual values that our algorithms, our methods, our program might be getting. Let's start with the simplest algorithm that we know. Let's start with our linear search, and this will help us make the ideas that we're discussing really clear. So I'm going to start by drawing my array as I've done many times before for a linear search. Let's see here. I'm just going to give myself 6 spots. I wish I had drawn my outer square to or rectangle to the right size here of the graph. There we go. That looks nice. Okay, and let's go ahead. We'll label our boxes. We have different indices. We'll just get this all set up the way that we always do. And let's just put some numbers in. 17, 22, 91, 101, and 50. I might as well stick with being increasing, and I can use this array again later. There we go, 151. Okay, let's start with linear search. Oh, I don't really want to be in green. I'll switch to blue. Linear search. Now imagine we're looking for a target number in our array, as we tend to do. Target equals question mark. What number would allow us to get our best case scenario? So now we want to find an O of 1 best case scenario. Well, looking at this, I know that if my target number is 1, when I run my linear search, I'll go look for it starting at position 0, and I will find it, and I'll be done. If the target is in the first position found target, we'll say, there we go. We just check once and we're done, right? That's a single comparison. So what we can say is that the time for the best time for a linear search algorithm over n values, looking for the target value, I don't have to say it like that. I can just say over n values is going to be 1, right? That's our best time. Awesome. Love that for us. What about our worst case scenario? Let me flip back over here. Well, in a worst case scenario, what input value would be resulting in us hitting the worst possible scenario? Well, if I look at my data here, what I can see is if I want to get the worst case scenario, I would have to start with looking over here and not finding it, here, not finding it, here, not finding it, and so on and so forth until I reach that last element or not find it at all. Either of those scenarios result in me checking every single element in my list. So in order to hit a worst case scenario, my target could be 151 or negative 2000 or anything that's not in the list, really, right? So to hit that worst case scenario, we are talking about last position found target, or the target does not exist. Either of those scenarios will result in the worst case time of our linear search over n taking n steps, right? What we can see is that even though the method never changes, the amount of work can vary drastically. And this is why we need to do a case-by-case analysis. You'll notice that this is different from the runtime, the asymptotic notation runtime, I mean, right? We're still talking in terms of big O because our growth of this algorithm is different than the running time of it. The growth of the algorithm occurs for an algorithm in general, in terms of as n gets bigger. But now we're talking about in terms of a given algorithm, how does the input affect the running time? What is our worst and best case scenarios for that? So these words can sometimes get kind of complicated and confusing, and it's really important to sort of highlight them in your notebook or whatever you're using so you can understand the difference between the growth of an algorithm and its runtime. They're not the same thing. Now we're going to step up to something maybe a little bit more interesting. We're going to move on to binary search, and this one will behave very differently depending on where the target is, similar to linear search, but different because it's a different algorithm. So what I'll go ahead and I'll do is I'll just pick this up right here, scroll down. I'll use my same array. There we go. And we can just continue down here with binary search. All right. So once again, let's imagine that we're going to be looking for a new target value. Let's go looking for target equals question mark. Well, our very first question, again, is how can we get that best case scenario? And what is the best case scenario? So what is the best case scenario? Well, the best case that we could possibly get here would be an O of 1. And we can see that it would be an O of 1 because just like our other search, if we find it on our very first check, we're good. If we go looking for a target value of 91, we split our array in half, we end up taking this value, we find it, we're done. That's O of 1. So just like a linear search, finding the element on the first run of your loop allows you to run in O of 1 time. Finding the element on your first loop check is one step. We did it. We found it right away. Now, the alternative is, again, of course, our worst case scenario, worst case. And when we ask ourselves, what is the worst case scenario here? Well, with binary search, it might be a little bit easier to imagine the worst case scenario, being that we don't find the number at all, just to sort of showcase this a little bit better. But it is the same, where it's either the very last possible checking element or we don't find it at all. Those two scenarios of what creates the worst case is the same. So I'm just going to write that down. Finding the element in the last possible checked value or not at all. Similar to linear search. Similar to linear. Okay. So what does that look like here? If I go looking for a 0, I start the same way as I did for the best case scenario. I check 91 and I see 0 is smaller. So now I take this subarray, split it in half, and I check 17. And here I can recognize, okay, I'm smaller than 17. So now I'll take this array and split it in half, and I check this value here. And I recognize I'm smaller than 1. And now I realize I've fallen off the array and I didn't find it. So what happened? Well, we threw out half the array each time. We've spoken about the runtime here before, and now we can really understand that this means that we have a worst case runtime of log, that's supposed to be a log, base 2 of n, because we're going to throw out half of our array each time. So this is roughly log base 2 of n. Now, unlike linear search, we do have the same best case, one check and we find it. But the worst case grows way, way slower. This is why binary search is incredibly efficient. And so even though both of these allow us to get a best case of O of 1, we can see that there's a very big difference between our worst possible case scenarios. And I'll draw a little graph in a bit to sort of additionally highlight this as we go on. Now let's look at a little bit more of a complex example. Let's talk about insertion sort, because this is extremely sensitive to input order in a way that we haven't really fully explored yet. So let's get this written out and see what the heck is going on. So our best case scenario for an insertion sort is kind of an interesting one. Imagine for a second that you are trying to sort books on the shelf at the library. Constantly having to pick up books and move them around would be exhausting for you. That would not be something that any of us would probably want to do, or at least not for very long. But if your job was to determine if they were sorted, and if not, use an insertion sort, and every single time you grabbed the next book in the unsorted portion and found, oh my God, it's already in the right spot, that's a really, really easy job. So our best case scenario, best case, is O of n, and it's already sorted data. And I will show what this means with a little example as well. Just a little one. We'll do this. Here's our array, and here are our values. If you recall, you basically start with a sorted array that looks something like this. This is the sorted array. And now what we're going to do is we're going to move our partition here and put this into the right position by shifting everything over. But what we find is it's already in the right position, so we don't have to do anything. So in our first run through, +1 step, but that's it. We only had to do one quick check, no shifting required. When we moved here, we found that we are also in the right position, +1 check, but no shifting required. And then we did that here, and we did that here. So we did that 2 more times with +1 checks, with no shifting required at any point in time. So where does this land us? This lands us with 5 elements and 4 checks. So an already sorted array or nearly sorted allows us to get really, really close to that O of n, right? We don't have any shifts that we have to do. 0 shifts occurred. So our best case for insertion sort is O of n. Let's go and look at the worst case now. Our worst case scenario is a little bit different. Our worst case, we have to ask ourselves, what kind of an array would result in the most number of shifts, the most amount of times that we would need to touch elements and shift them around? Well, hopefully after seeing an already sorted array being the best case, your brain is trying to think right now about sort of how can we take the opposite of this? And the opposite of a completely sorted array like this is not actually unsorted. It's sorted in the reverse order, right? So this is saying the opposite of sorted is unsorted is technically a true statement. But really what we're looking at here is something that's sorted, but in ascending order. What I need now is something that's sorted, but in descending order. Let's take a look at what that might look like. 5, 4, 3, 2, 1. Now let's go and run through each of the steps just as we did before, like these, with our number of checks and shifts that we had to do, and see what's going to happen. As soon as we grab that first element and we try to figure out what position it needs to be in, we realize a shift has to occur. These two have to switch spots, right? So the 4 and the 5 will switch spots. We did our check, 4 and 5, and we had to do a shift. So up here, I wasn't really counting shifts. I just counted checks. If I want to count checks and shifts even, we could say. Here, if I do checks and shifts, I had to do 1 check and I had to do 1 shift. All right. Then this line moves over here. And we realize that this needs to shift over here with a check and a shift. And it's going to have to move over here with a check and a shift. So we end up with 2 checks and 2 shifts. So we end up with another 4 in our count here. Let's reorder. Whoops. Let's reorder these. I shouldn't have put that line right on top of my line there. That's okay. There we go. Let's do 1 more here. We grab the 2 and we realize we have to do another check and shift, check and shift, check and shift. So this is going to be 6 more in our adventure toward a sorted array. We've got 2, 3, 4, 5. And then finally, we do our very last element and same thing, check and shift, check and shift, check and shift, check and shift. This gives us a count of 8 sort of interactions with our checking and shifting elements around, leading us to our sorted array, 2, 3, 4, 5, and a total of 20 check shifts for 5 elements. Now, this isn't quite n squared, but if you recall, for 5 elements, n squared would be 25, right? So we're getting pretty close to that n squared growth that we would expect to see in this kind of an algorithm. So this work is typically, as we've seen before, described as big O n squared. And our worst case we can now say is n squared. So we've now identified a best case running time and a worst case running time. If our data is pretty much already sorted, insertion sort is fantastic. It works really, really well for us, but it's terrible when our data is in reverse. And when we do our case analysis, we can see exactly why that's the case. Now, let's talk about the average case for a second. And really what we're going to just touch on very briefly here is a common misconception. When we're talking about average case, I don't mean average in the mathematical sense. Average case is not halfway between worst and best cases. That is not what we're talking about here. When you do an average, like a mean in stats, you take all the values, like a 10 out of 100 and a 90 out of 100. You get 100, you divide it by 2, and you realize that you got a 50% average. So if 2 students, this is student 1, gets 10% on the test, and 1 student gets 90% on the test, it's a 2-person class, we see that we sum them up, divide it by the number of students, and we get a 50% average. We can also see that this isn't super indicative of what the data actually shows us, right? Means, averages are incredibly susceptible to things like outliers. So when we're talking about average case, we're not talking about halfway points. We're not talking about allowing our data to be susceptible to outliers like this. That's why the word average is like a little bit sketchy to use here. And more often than not, I try to also use the word typical case. Because what we actually want to do is consider a graph that looks like this. Some of our data, like already in sorted order, is over here. And some of our data in reverse sorted order is over here. But the bulk of the work that we do will happen over here in the average scenario. For example, if you had to look through a literal phone book and 99% of your searches through the phone book could use binary search, 1% was like weird corner cases that just like really didn't work out that well for you, your average probably shouldn't be halfway between a binary and a linear search, right? That's not indicative of the work that this algorithm can do for you. The average behavior is entirely dependent on the probabilities, not the arithmetic midpoint. They're totally different. All right, let's summarize. We've now seen that the same algorithm can behave very differently depending on the input. We have our best case being minimum work, our worst case being maximum work, and our average case is more of the expected or typical input work. We also looked at understanding cases and how this can help us choose what algorithm we want to use in a really intelligent and science-backed way. We have the vocabulary to understand variability. And next, we're going to combine all of this, these growth shapes, these input sizes, and case behavior, so that we can figure out when we should use different algorithms and when they will truly shine. Thanks, everybody, and I'll see you in my next video.